So steady, done. Just done actually a few minutes ago. So the course could have started here, but we really wanted to review these concepts. That the lift on airfoil with an angle of attack is really due to a circulation. So we spent some time defining what is circulation in the first lecture, what is vorticity in the second lecture, what is the lift, Kotta-Joukowski lift theorem that L equals rho u gamma, we derived it. What's the story of CL equals 2 pi alpha, right? Now we just reviewed the thin airfoil theory. So, like I said, all these concepts you have seen before, but we need these concepts, the law of zero total circulation, the conservation of circulation, the meaning of circulation first, then the conservation of circulation. The lift is due to circulation. What is vorticity and its relation with circulation? We need all these concepts fresh and vivid. So please, if you don't have them fresh and vivid, you need to go back and watch the lectures, lecture video recordings, lecture 1, 2, 3. Any question about these things? Because today we will have our we will do unsteady dynamics today. Okay, so this is unsteady. If I'm bold enough, I could have started here this lecture. Any question before going into unsteady? So we learned that CL is 2 pi alpha. I'm going to review a little bit from the first lecture. So perhaps you remember this, that what is unsteady aero descriptively? If I have angle of attack as function of time in the following form, 0 here and then a jump in the angle of attack, which we're going to study in detail, maybe 5 degrees, then what's the corresponding lift? If I am to plot a similar curve for the lift coefficient, if I exactly follow the quasi or the steady formula, which is 2 pi alpha, 2 pi times 0 is 0, and 2 pi times 5 degrees is 0.55. Okay? But the lift will never jump instantaneously. You're giving an input, changing the angle of attack, and here is the output. It will never follow the input instantaneously. There is some dynamics, there is some lag. The lift will take some time to build up. So this is the unsteady lift behavior, and this is our interest in this course. First of all, to acknowledge that the lift will behave this way. Second, to understand the physics, how the lift behave this way. Third, and more importantly, to mathematically model it, to develop a model, a mathematical model that predicts the evolution of lift. Okay? So this red behavior is the steady behavior. Sometimes we call it, or usually, typically, we call it the quasi-steady behavior, meaning that we are using the steady formulas, 2 pi alpha kind of thing, with an unsteady motion, assuming that unsteadiness is not apparent. Yes, Leo?
Is it correct to say that whenever an object is changing its angle of attack, first few seconds or so, whatever?
Exactly, yes.
Okay.
The very early moments, you don't get the steady formulas, for sure. But if you don't care about this very few moments, because they are really fast, so for an airplane flight dynamics, the airplane is so huge that the time taken to move the inertia will outweigh by far the time taken to accelerate the aerodynamics. Okay? So the inertia of the airplane makes its time constant much larger than the time constant of the aerodynamics. So it's typically, we neglect unsteady aerodynamics even if we're dealing with time variation of airplanes. So airplane flight dynamics 175, it's all about the airplanes changing its motion, right? But we typically neglect the unsteadiness. Because for a conventional airplane, that's a very legitimate assumption. If it's a fighter airplane, though, in a very aggressive maneuver, then you might think, no, we should account for unsteady airplane. If it's a pure unsteady phenomenon, even if it's a conventional airplane, Boeing 737, and you have its wing, and it's going into a flutter, the phenomenon itself is an unsteady phenomenon. And we're going to do it in detail in this course. You will see that if you use 2 pi alpha kind of thing, any quasi-steady or thin airfoil or whatever, to determine the flutter, you will get the flutter boundary very incorrectly. You will get a very different speed than the flutter speed if you use unsteady aerodynamics. Okay? So descriptively, this is what is unsteady aerodynamics. If you have a question, please stop me. Mathematically, so this is first thing, descriptively, mathematically, or math-wise, again, we mentioned this in the first lecture, but we need it now, after we become so mature with this review. Mathematically, is that the CL alpha relation is not algebraic anymore. CL alpha is not 2 pi alpha, even if you add nonlinearity. Okay? Even if you add, and you just seen that, even if you add alpha dot dependence, even if we're saying, okay, what about, so this point, what do I mean by this point? I mean, how to judge whether a given model is an unsteady model or not, from the get-go, without studying anything. You give me 2 pi alpha, of course it's not unsteady. Why? Because you dictate that an instantaneous change of alpha is associated with an instantaneous change in the lift. The same here. Alpha dot is 0 and alpha is changing its head. Or even if alpha is 0 and you're relying on alpha dot effects. Again, if you have an instantaneous velocity for the wing, it dictates an instantaneous lift. This does not happen. No matter how you add alpha double dot, alpha triple dot, I don't care. The relation, the true relation between CL and alpha, rather, it's a dynamic relation. And you pick the way, you pick your poison. You pick the way how to represent this dynamic relation. Typically, in our undergraduate system dynamics course, we typically describe dynamic relations between mass spring or whatever by differential equations. Typically, if you're lucky enough, it's ordinary differential equations. If you're not lucky enough, it's a partial differential equation. So a relation like this, CL dot equals negative 3 CL, negative CL, say, plus 2 pi alpha. If somebody is proposing a model like this, I cannot reject it from the get-go. Why? Because this is an unsteady model. Why? Because if you start with an initial condition 0 lift, and you apply 5 degrees step input, you will not get an immediate change in the lift, but an immediate change in the lift rate of change. So that if you maintain your input for a while, i.e. maintaining this guy for a while, then the lift will build up. Okay? CL dot for some time will give you CL later on. Okay? And you can do it whatever you like. You can do it maybe like this, or about CL double dot plus 3CL dot plus CL equals 2 pi alpha. Again, I cannot reject it from the get-go. Maybe it's a legitimate unsteady model. You need to study it now. Okay? So this is how to judge a model whether it's unsteady or not, because this is, believe me, this is quite confusing. Many people, don't want to say experts, but practitioners in the field, when they see this, they think that this is an unsteady model because it depends on alpha dot. No, it does not. Okay? It's not an unsteady model. This might be. And any equivalent form, or any equivalent form. What do you mean by an equivalent form? You guys know it, and we did it in the first lecture. So a dynamical system can be described by a transfer function, which is the Laplace transform, linear dynamical system, which is the Laplace transform of the output, my left as a function of S Laplace, divided by input, my angle of attack as a function of S at zero initial conditions. If you give me a transfer function, dynamical system transfer function, I will very happily accept it. Or equivalently, state space model. You give me some states, maybe x is x1 up to xn, x dot equals A matrix times x plus B matrix times your input u. My input, now we know that my input in aerodynamics is the angle of attack, alpha or alpha dot whatever, you can pick the right input. And your output y, now it's the left, is Cx plus du. This is a standard state space model where my input is the angle of attack, my output is the left. If you give me a model like this, actually these are perfect models. Or if it's a linear, if it's a linear system actually, from a system identification point of view, you can give me the step response. What's the step response? It's exactly this curve here, this green curve. You have a step input. What is the transient output due to a step change in the input? So this is CL as a function of time. If you give me this relation only, I can get any of these. I can get this very quickly. How? Well, this is the output as a function of time, right? Please do a Laplace transform for it. If you give me an analytical expression here, maybe e to the t, 1 minus e to the negative t, for example. This is an expression for time. If this is CL as a function of time, do Laplace transform. I get CL as a function of s divided by 1 over s, because it's step input. I get the transfer function, right? Actually, this is how we will do a transfer function later for this exact system. Okay? Or frequency response. Now we're going to talk about this today in more detail. Long story short here, this is the Booty plot. If you are a dynamical system person. So, which is two plots, it's not one. Both from the transfer function, magnitude versus omega, phase versus omega. Now we're going to talk about it in detail later. But pick whatever dynamical form that can represent a dynamical system and give it to me. So this is our objective in this course, is to develop such a model. Okay? This is the objective. If you're developing an unsteady aerodynamic model for your research, this is the objective, is to develop one of these guys. Okay? Any question, please? So we learned what is unsteady aerodynamics. Descriptively is that the lift cannot change instantaneously. Mathematically, we now know what do we mean by unsteady model, and we're going to talk about modeling wise. And for modeling wise, we're going to discuss now for the first time the most complete description of how lift will build up, how lift builds up. So yeah, because if you want to do modeling wise, by modeling wise I mean, so this is the sought form, the desired form. Okay, how are you going to do it? Well, you can do it empirically, you can do it using neural network, you do it whatever you like, but we are in fluid mechanics course, we're going to do it in a theoretical aerodynamic point of view. We're going to develop it from a fluid mechanics point of view. So if you want to do it this way, we need to understand the physics, how the lift builds up. If you understand this, then maybe you will be able to develop a model for it. How does lift and circulation, you already know that lift is due to circulation, build up? Yes, Leo?
How come we're just talking about lift and not things like drag for airplanes?
Well, they are associated because they both come from almost from the same origin, but we're more interested in lift because lift can be like what we did throughout the past lectures. We managed to determine lift from almost inviscid arguments. We needed one argument to account for viscosity in an indirect way, which is the contact condition. But other than that, all the analysis is irrotational. So you have a linear equation, you can do a lot with math. We did a lot actually, right? Drag is the same. I mean, there are two major types of drag, right? The drag due to lift, so if you got the lift, you can get drag. But then there is the viscous drag, right? And the viscous drag, then you lose this rotationality from the get-go, so you don't have much luxury in mathematics to deal with. But we have our theories. You have the boundary layer that you can deal with, okay? So if your interest is to capture the drag from the beginning, you will not go very far, okay? It's not very much known about drag. Yes, Anchit?
What physical meaning does the phase tell you for?
Lag, it's lag.
So like how much time?
Yes, we'll talk about it in a minute. How lift builds up. Now we are mature enough to get this. Let's see, to discuss it at least. So before proceeding, I'd like to show you this. This is by Houghton and Carpenter, Aerodynamics for Engineering Students. It's a good book, and you can read this. This is just excerpted from the book. There is no fully convincing physical explanation for the production of the starting vortex and the generation of the circulation around the airfoil. Of course, generation of circulation meaning how lift builds up, okay? Because lift is due to circulation. I agree for almost 100%. Hopefully we will have convincing enough argument. It's not fully convincing, but... So let's see. We have T equals 0, my airfoil, no U infinity, okay? And I will take a contour around my airfoil, C, okay? This is contour, closed contour. What is gamma of that contour? What's gamma C? 0, we have nothing, right? And I will start the flow suddenly. So this is T equals 0 plus in the very first moment, and I have U infinity. So this is your airfoil, and here is my U infinity with some angle of attack, okay? T0 plus is the very first moment, right after you start your flow, okay? The flow